Okay, how does the Tacoma bridge model work? We've got these horizontal members that are rigid bodies, just really rigid rods that can librate, that can vibrate torsionally about their equilibrium positions, like this. See that one go? They're also connected through the middle by torsional members. I'll just put the axes on here, and the torsional members transfer a little bit of that torque, the twist, from one member of the bridge to the next. So if I start with, let's solve that again and run it again. If I start with one member of the bridge bent a little, let's say a truck was driving over it or something and moved on, it will experience a damped oscillation, settle down to a horizontal position, which I'm not a civil engineer or an aerodynamic engineer, but horizontal is really good when you're talking about something you want to drive on top of. So let's plot that the excursions of this element, which is called segment 3, and which is oscillating. We want to plot segment 3's angle. Theta is the name of the angle over time. That's segment 2, which picks up a bit of oscillation from segment 3 and then finally damps down. Segment 3 itself, though, starts with a lot of oscillation that is damped, that dies down. If we look at segment 1, presumably it'll have take an even longer time to get going and be even lower amplitude. There you go. Then segment 2, because again the oscillation in the one that we actually drove the truck over, which is purple, takes time to transfer its energy to these other members. And the whole structure is damped. I've lowered the damping considerably from what probably is realistic. This is a pretty highly tuned bridge. The reason is just so that you can see what I'm talking about here. It should probably be considerably more highly damped. That doesn't affect the physics of the flutter a whole lot. Let's increase the airspeed though. Here's an airspeed of 2.2, same setup again. You can see again segment 3 taking some time to damp down to level. And the concern here is not that I've made the bridge more resonant than a real bridge would be. It's that the restoring force is dropping, and that's why the bridge is taking much longer oscillations. It's not really taking longer to damp, but it's an oscillation period is taking a much longer time. That is a surprisingly bad sign. So here's another plot of segment 3's angle. 1, 2, 3 cycles of oscillation in the first time division. All the time divisions are the same on every plot. So we went from about 7 oscillations per time division to 3, less than half. That means that the restoring force is less than a quarter of what it originally was. To peek ahead a little bit here, restoring force is what keeps the bridge horizontal. Okay, airspeed is 2.45. At some critical value, the restoring force will go to 0. And I'm trying to creep up just under that critical value. You can start to see, though, behavior that's reminiscent of what's in the movie, but it doesn't run away. It does just barely damp itself. Easy to make, which is an important feature. Once I cancel out the 2 simple first-order restoring forces that I've actually plugged into this model, I have nothing left. Whatever determines the behavior of the model is other higher-order terms that I haven't even thought about, or certainly not very much, and I haven't gone and made an effort to select all the important second-order terms. So the model, while it'll show instability, what happens during the instability is really almost unmodeled, and you're in a garbage in, garbage out situation. That's unavoidable in modeling. But of course, in back of the envelope modeling, you're right up against it all the time because you're trying not to do unnecessary work. Here's the angle when you're above the critical wind speed, and it never does return to horizontal. The system no longer prefers to be horizontal. There's not a restoring force. And also look at numerical data on this. Here's the numerical data window, and I can go across and look at segment 1's variables are listed first. There are ways to suppress some of this so that I don't see quite as many columns, although just sometimes you need them. Segment 3's angle is this column here. Continue. All right, thanks for watching.